Okay, we can start. The aim of today is first of all to close the part on the Greeks, and then we are going to enter in discussing the trading strategies, devoting ourselves today mostly to directional trading strategies on the price of the underlying. But first of all, let us finish the part on the Greeks. We have seen delta, gamma, and theta, and the key Greek which is remaining is Vega, which can be defined as the partial derivative of the market value of the option portfolio as opposed to changes in the level of implied volatility. So Vega approximates the ratio between a discrete change in the market value of my option or option portfolio relative to a change in volatility. Based on this, we can have what we can call a Vega effect, which is the change which is driven by Vega, which is equal to Vega times the change in the level of implied volatility. And the first point is understanding when Vega is positive and when Vega is negative. This is pretty simple if we think back again intuitively to the picture of the option value as a function of time and intrinsic value that we derived at the very beginning. For instance, imagine we have a call option strike 140, and imagine we have the future price trading at 136. We have a certain amount of value, which is time value here, which has to do with the chances that the option might be exercised before maturity. And what happens if volatility increases? If volatility increases, if volatility increases, the effect is that the whole curve is moving up, because when the option is out of the money, the chances that the option may become exercisable increase. And specularly, when the option is in the money, the chances that the option may be abandoned increase. So this would be the effect of rising volatility. Instead, specularly, if we had a reduction in volatility would imply the curve going down. A similar effect would be valid for put options. In case of put options, again, we have the curve, and clearly the curve would move up if volatility increases, and down if volatility decreases. It's not going up and down in a parallel fashion. Sorry for the quality of the picture here, which is imprecise, also due to some problems in the pen, actually. But the key idea is that a higher volatility implies that time value is increasing, so the option is worth more. Lower volatility implies that time value is smaller, and so the option is worth less. This is important to clearly capture super easily, which is the meaning of being Vega positive and being Vega negative, and which are the guys who are Vega positive rather than Vega negative. Being Vega positive means that if you have a plus here, the case in which you make money, so in which your change of your market value of the portfolio is positive, is when volatility goes up. So being Vega positive is equivalent to saying to be bullish on implied volatility. And this position of the guy who makes money if volatility goes up is the position of the option buyer. Why? Because we've seen through the graphs that an increase in volatility implies a higher price for the option value. And of course, this is good news for the buyer and bad news for the seller. Specularly, if you are Vega negative, it means that if you have a minus here, in which case do you have a plus here? So in which case do you make money? Only if volatility decreases. So being Vega negative is equivalent to being bearish on implied volatility, and is the position which is typical for the option seller. This is step number 1. Step number 2 is understanding whether Vega is higher for at the money versus in the money or out of the money options, as we did for the other kind of Greeks. Here we can have first an intuitive idea, and then it could be a little more sophisticated, and I would do both. So in terms of intuition, imagine again that's a call 140, and let us compare two very distant prices, say 120 and 160, where the option is deep out of the money or deep in. We want to eventually end up trying to have a graph of Vega as a function of the moneyness, of how much in the money or out of the money the option is, of the moneyness of the option, which we measure now by F divided by K. So where we have F divided by K equal to 1, the option is at the money. Same story as we did for the other Greeks. Now, the intuition is the following. When you are at, say, 120, so tremendously out of the money, the option value is going to be very, very close to 0, very small. Of course, if you have an increase in volatility is slightly higher, but say volatility goes up from 7% to 8%, you don't have a situation in which the chance of exercising the option becomes from 0.1% to 7%, okay? So you are so desperate if you want that even an increase in volatility doesn't help much. Instead, the impact of a change of volatility is much higher if, for instance, you are here or here, so pretty close to 140. That's a situation in which you still have already a significant chances of potential exercise or potentially abandoning the contract, and the higher volatility has a far larger effect on the potential final result. So the first intuition is that you must have a situation in which, again, you tend to have a peak Vega around the at the money case. At the money options should have a higher Vega than out of the money and in the money options. Sorry if the graph is not symmetric, let me do that better. So more or less something like that. And the second part of the story, as we did for the other Greeks, what happens when you get closer to maturity? Now, when you get closer to maturity, this curve is falling down even more. And it is pretty intuitive that if at 120 you were close to desperate with very little value of the option remaining, if you were, say, 2 months to maturity, if you are 2 weeks to maturity, it's even worse. If you are 2 weeks to maturity, an increase in volatility is even less relevant and significant. So you must have a lower Vega. The same thing happens here at 160, where the risk of abandoning the contract is already super negligible, and it's even more negligible if you are 2 weeks from maturity. So even an increase in volatility is not substantially changing the option value. So the option is not so sensitive. Now, what happens instead when you are at the money? Now, when you are at the money, if you remember, for instance, the profiles of gamma and theta, where you are at the money and close to maturity, you have higher gammas and higher theta. This is not the case for Vega. So Vega would be systematically decreasing when you get closer to maturity for any possible level of moneyness. Why is this the case? In order to understand that, think about the case in which your parents sold you a call option strike 140. and imagine volatility is 7% and goes up to 8%. Of course, this is good news for you if you are an option buyer, fine. Or if you had the option as a present from your parents. But now let me ask you the following. Do you have a stronger impact on the option potential, if you want, and as a consequence on the option price, if when there is this increase in volatility, the number of days remaining is 90 days, or if the number of days remaining is 2 days? If you have only 2 days remaining, even if volatility is higher, it's going to be higher only for a very short amount of time. So essentially, you don't have enough time to truly exploit the good news of higher volatility. Whereas instead, the relevance is larger if you have many more days to go to maturity. And having many more days to go with a higher volatility is far better news, okay? So the intuition is that the sensitivity to volatility is going to decrease systematically as you get closer and closer to maturity. Now, hopefully, this intuitive story should be okay and sufficiently clear already. And this is the only way in which you can explain this to a colleague which doesn't have any technical background on Black-Scholes. Since you have that, we can also be slightly more refined in terms of intuition, even without running the full derivative. When you consider the Black-Scholes price, the price of Black-Scholes for the call option can be written as S times n of d1 minus k discounted, so times e power minus rt, multiplied by n of d2, where n of d1 and n of d2 are the values of the cumulative function of the standard normal calculated in d1 and d2. And d2 is equal to d1 minus sigma times the square root of t. Now, first point that I want you to notice is the following. Since n of d1 is in the positive part of the option price, and n of d2 is in the part with the minus in front, the larger is the difference between n of d1 and n of d2, and the larger is the option value, okay? So a larger difference between n of d1, which is in the positive part, and n of d2, which is in the negative part, is going to be good news in terms of the option value. Second thing I would like you to notice is the following. Which between n of d1 and n of d2 is going to be larger? It's pretty simple, because it depends on which is larger between d1 and d2. If this is the density function of the standard normal, since d2 is d1 minus something, it means that d1 is on the right relative to d2. In this case, I'm picking them as symmetric relative to the 0. Of course, this is not necessarily to be taken for granted. This is not absolutely the normal case. But what I'm saying is that d2 cannot be here. D2 has to be on the left-hand side relative to d1, okay? So in this specific case, for instance, this area would be coinciding conceptually to the difference between n of d1 and n of d2, if you think about it, okay? Now, let me add two elements. First point, an increase in sigma has the effect that the distance between d1 and d2 widens. And as a consequence, the distance between n of d1 and n of d2 widens as well. But the impact of the widening of the difference between n of d1 and n of d2 is not the same depending on where you have d1 and d2. So consider three different possible cases. One case is the one in which d1 and d2 are here on the far left of the distribution. Let's call this one as A. One case is B, which is the one I've already drawn, in which D1 and D2 are relatively symmetric to the center. And the third possible case, I'm taking just the most extreme ones, is the ones in which D1 and D2 are here on the far right of the distribution. Is that okay? Now, this region would be the difference between n of D1 and n of D2. And if you have a shock in volatility, let's say volatility going up, what you have is that these two are more distant among each other, and as a consequence, this difference is widening. Now, think about it. In which of the three cases, A, B, or C, if you have an increase in volatility and the distance D1, D2 widens, you have a larger effect in terms of widening of the distance n of D1 minus n of D2 in A, B, or C. This is going to happen precisely if you are in case B. Why? Because in case B, there is the density function is particularly high here. So if you just increase the difference by little, the region behind that is far larger than, for instance, if you increase by the same difference here or here. Is that okay? Now, case B is actually when the option is at the money. How can we say that? Intuitively in this way, D1 is the natural log of S divided by K plus R plus half sigma squared times T divided by sigma square root of T. Okay? And we can rewrite it as the natural log of S times e power RT divided by K plus half sigma squared times T divided by sigma square root of T. What I've done is a simple trick in the sense that RT can be written as the natural log of e power RT. And then since the sum of two logs is the log of the product, you can take this in this way, okay? Similarly, if D2 is equal to the natural log of this is D1, plus sigma squared times T divided by sigma square root of T minus sigma times the square root of T, you can easily rewrite that in this way as the natural log of the spot multiplied by e power RT divided by K minus half sigma squared times T. Okay? Now, if you look at this formulation of D1 and D2, you can see pretty easily that the case, for instance, in which D1 and D2 are perfectly symmetric around the zero is the case in which this natural log is equal to 0, okay? Which means the case in which the forward price divided by K is equal to 1. So when the option is at the money forward. So the intuition is that when the option is at the money, you are precisely in this case in which a change in volatility is going to have a much wider effect on the option price. Instead, if you are in case A, you are in a situation in which this component is not around 0, but is sharply negative, which is the case in which the spot price is very low. So even S times e power RT is much lower than K, so the option is out of the money. Instead, case C is when this log is very positive, so when the option is in the money. And the intuition that we get from here is that you must have a larger sensitivity to sigma precisely when the option is at the money, okay? However, as I said earlier, if this slide were unclear, you can still survive and just keep the intuitive explanation that we had here. I would be satisfied in any case. Just a different way to remember clearly what is happening truly to Vega. The second part of the story is that for the sensitivity to Vega of being closer or more distant from maturity, you can observe easily that whenever you have sigma in the Black-Scholes formula, it's never alone. It's always multiplied by the square root of time. It is what is happening here. It is what is happening here. And even sigma squared times t is actually sigma times the square root of time with everything squared. So the intuition is that a change in sigma has an impact which is a function of the square root of time. If the square root of time is small, even a change in sigma is going to have a smaller impact on the option value. So as t gets closer and closer to maturity, the impact of Vega becomes smaller, not in a linear fashion, in a square root of time fashion, so the biggest decrease is in the very last few days, but it's systematically decreasing as t is becoming shorter, smaller and smaller. That's the intuition. So this is the behavior for Vega, and getting back to the slides where we also have the graphs on the Greeks. For instance, this is a graph for Vega, where, as you see, the Vega for the longer maturity, 3 months, this one, is with a peak around the end money, and when you get closer to maturity, it is systematically going down for all possible levels. This is what happens as time passes. Okay, in order to finish up with the Greeks, there are only a few more things to be said. Very quickly, to a couple of things on raw, but as essentially on raw, the only thing I need is that you can remember what is written here. So raw is the sensitivity of the option value to changes in the risk-free rate. Is the partial derivative of the market value of the option relative to the risk-free. Okay? This is the key thing. The reason why we don't spend truly time on raw is the fact that, as I mentioned already quickly, the impact of the risk-free rate changes a lot from one option to another one, depending on many different factors, whether the premium is paid upfront or at maturity. If the option is American or European, we have a slightly different effect because the European option is particularly linked to the forward price, which is sensitive to the risk-free rate. It matters also whether the option has an intrinsic value or not. And there are many, many, many different cases. So forgetting for simplicity for the intermediate one, which doesn't really matter, just consider 2 extreme cases. The first one is the one we already mentioned of Bund future options, where the premium is not paid upfront, is paid at maturity, and the underlying is directly a future, and here ROI is completely irrelevant. For this contract, the risk-free rate does not even enter into the pricing model, so you don't have a RO. It does not exist, a derivative to the variable, because the variable is not entering into the pricing formula. On the opposite extreme, you have currency options, which are typically European style, typically on top with the premium paid up front. And here you have 2 different ROs, not 1, but even 2. The RO relative to the domestic rate, so this is RO D, and RO F, which is the RO relative to the foreign rate. Why is this the case? Because when you have a forward currency rate, the forward currency rate depends on the spot rate, on the domestic interest rate, and on the foreign interest rate. So in this case, for this option, you have 2 interest rates that have an impact on the option price, and you need to have 2 different ROs. So, but the key idea for me is that I'm satisfied if you know what RO represents, nothing else, and you are aware that if you will start working on options, it's important that you learn how the raw for your contract is working, given that the behavior may change a bit, sometimes substantially, from one contract to another one. The last thing that we have to say on the Greeks is to explain how you can use them potentially and which are the potential limitations in assessing the effect of multiple shocks together, of price of the underlying volatility and time. Because when you do that, which is something that is important for traders, but is also important for a risk management perspective, you can have potentially two different methods. The first one is called partial revaluation. The second one is called full revaluation or repricing. And I want to make sure that you know what these two things mean when working outside in the finance world. Partial revaluation is when you estimate the change in the market value of a portfolio of options through partial derivatives. So you estimate through the Greeks. For instance, through a delta gamma vega theta approximation as an example. The alternative is when you do a full revaluation or repricing. Let me clarify the difference. Having partial revaluation is when you combine the effects of delta, gamma, and vega as a list, or maybe delta, gamma, vega, and theta, and maybe rho if it also matters, in order to model what is the change in the option value. So, example, you say, imagine that the future is moving from 140 to 141. So you have a delta price of +1. Imagine you have volatility moving from 10% to 940%. So you have a delta sigma of minus 0.60%. Imagine you're moving from, in terms of time, from March the 9th to March 16th. So you have a change in time of 1 week, okay? Then you use this delta P, delta sigma, delta T, combined with the appropriate derivative. So delta times the change in the price of the underlying plus gamma divided by 2 times the change in the price of the underlying squared is the delta gamma effect approximation of the impact of the change in price. Then you add up what derives from the change in volatility, vega times delta sigma, and what is the effect of 1 week that has passed, as theta times delta t. The point is that we must be aware that the total effect that you can obtain can be different from the true effect in the option portfolio. Why? Because you are using partial derivatives. The logic in a partial derivative is to calculate the derivative of a function of multiple variables as if all the other variables were not changing. So they approximate better what happens if only, say, volatility changes and the price remains untouched and time does not change. If you instead are using them to combine multiple effects, maybe also multiple not so small effects, of course the approximation you get with this formula can become worse and worse as the effects become larger and larger, and especially if you have a portfolio of options for which Greeks tend to be volatile. So for instance, just a small increase in price changes the vega a lot, or a small change in volatility changes delta and gamma a lot, which can potentially happen in certain circumstances. The method which instead is more precise is to go through full revaluation or repricing, which essentially means you take your pricing model first with the initial situation of price of the underlying volatility and time, and then you rerun the model with the new data. So you take the difference between the market value calculated with the pricing model with the final price, final volatility, final time, which would be this column, the final, minus the price that you calculate with the same pricing model based on the initial values of all the variables. If you want an analogy, it's the same story as for bonds. If you have a bond that is now evaluated with a 1.5% discounting rate, so 1.5% is the correct yield for the bond. If you have rates going up to 2%, you know that the price of the bond is going to fall. How can you model how much is going to be the decrease in the price of the bond? There are two ways. The first one is repricing. So you take the cash flows of the bond and you discount the cash flows of the bond with 2% rather than 1.5%, and then you take the difference. This is what we are doing here. So we have the pricing model, which for the option is Black-Scholes. For a bond is taking the cash flows and discounting, and we compare the price before and after. In the case of a bond, for instance, the alternative would be to use modified duration and convexity to approximate how the bond price reacts to a changes of, say, 0.5% in the discounting rate. This is an approximation through derivatives, which would be the equivalent here of using partial revaluation. So in many cases, you can choose between a precise estimate or an approximation. Of course, this is using the full revaluation or repricing is always more precise. So this is the choice that should be preferred even by risk managers whenever this is feasible. So whenever the price for the option is not too complicated to be calculated, essentially. Now, final messages on the Greeks. First, they are the key indicators for the trader, and they're also relevant for risk managers. Keep in mind that most option trading desks are actually controlled, first of all, with limits in terms of delta and vega, rather than with limits of value at risk. The key limit is essentially delta and vega, maybe gamma sometimes, but essentially delta and vega. Second point, you can always derive them at portfolio level as the sum, the weighted sum of the Greeks of the individual options. So for instance, the idea that the delta at portfolio level is simply the sum of the deltas of the different options times the number of contracts, where we should remember that the number of contracts is negative when we sell, key idea of how derivatives, the Greeks at portfolio level work. Third idea, let us remember they are derived as partial derivatives of an option pricing formula. This has two implications. First, if you have different formulas, you have different Greeks because they're a partial derivative of a different formula. So remember that delta, gamma, and vega behave more or less in the same way across different contracts. Whereas, for instance, theta and even more, rho, can differ quite a bit between one contract and the other one. So for instance, the questions on theta that you will find in the exam as well are concentrated on options on Bund futures because they are far easier, whereas instead delta, gamma, vega can be done on basically any asset. And the second thing is what we just discussed, that they can be more imprecise if you want to model through the Greeks with partial evaluation a joint shock of more than one factor at a time. So keep in mind that if you have big shocks and big multiple shocks, you are not so sure to be super precise if you just use an approximation based on the Greeks. That's it for the Greek part. Even if we are going to use Greek extensively also in our next step, which is looking at directional trading first and then volatility trading. In this part, incidentally, I'm going to use a bit the slides, also because in the slides I've placed inside some exercises that I will ask you to try to work on, trying to have, if they work, because they don't always work, some nice polls through Blackboard to let you answer. Otherwise, I will ask you to answer on the chat. Now, let me first make an introduction. As an introduction, we have seen that the premium of an option is depending from many factors. So the price of the underlying, which can be a spot or a forward price depending on the type of option, the strike price, sorry, here I've used AE as exercise price, but the typical notation is K, as we did also previously. It can be volatility, implied volatility, so sigma, time to maturity, the interest rate, many other elements. Now, out of these elements, clearly two are particularly important from a trading perspective, and they are the price of the underlying asset and the implied volatility. Why these two are particularly important? Well, because they vary, the strike price does not vary at all, and so we don't care. And because these two elements are uncertain, so you can have people betting tomorrow having a higher price or lower volatility, whereas, for instance, on time to maturity, which is also relevant, the effect of what happens is going to be totally deterministic. So if today is the 9th of March, tomorrow has to be the 10th of March. So it's important to account for the effect of time in the strategies, but it's not something on which you can bet that tomorrow is going to be the mid of December, okay? So when you take a position, for instance, buying a call option, you are actually taking an exposure to different risk factors, at least underlying price and volatility. You typically associate buying a call option to being bullish on the price of the underlying, but for instance, you are taking also a position on volatility. Whenever you buy an option, you are Vega positive. So you're also betting on volatility going up. Now, of course, you can have situations in which, as a trader, you have a view on both elements. So you have a combination of expectations about what's going to happen to volatility and what is going to happen to the price of the underlying, but sometimes you have a view only of one of the two elements. And as a consequence, you might be willing just to take a position on the underlying price, or just take a position on implied volatility with little or no exposure to the other element. This is what identifies, at least in theory, directional trading strategies as opposed to volatility trading strategies. Directional trading strategies are strategies in which you essentially want to bet on the change in the price of the underlying with little exposure to volatility. So strategies in which you have a large positive or negative delta and a small Vega, essentially. On a volatility trading strategy, you want to have a big Vega position and a small delta position. So big exposure to volatility, little exposure to the price of the underlying. Of course, in practice, risks are really not so frequently totally isolated. And I'm also going to show even today that you can have, for instance, a directional trading strategy in which you want to pick a small exposure to volatility. Still, you try to reduce at least the other exposure and have a main exposure and another one which is small and limited. And the distinction helps a lot in presenting the main trading strategies. Here, we are not analyzing hundreds of trading strategies. There could be a lot of them. We are analyzing only a few ones, the most relevant ones, but we are going to study them looking at the Greeks of the strategies and understanding how the Greeks change, which is the thing I consider to be most important. If you understand in a decent way or fantastic way what we are talking about here, then you would be able to evaluate even strategies we are not going to discuss here quite easily. In order to introduce the idea, let us imagine we have a trader that believes that the Bund future price is going to rise over the next weeks. So he's going to be bullish on the price of the underlying. But he or she has no views on implied volatility. He or she doesn't know where the implied volatility is going up or down. As a consequence, what's the problem? The problem is that the typical strategy of somebody who is bullish on the underlying and wants to play with options would be to buy a call option. But if I buy a call option, I'm jointly taking an exposure to delta, so to the price of the underlying. I'm delta positive, and this is fine because I'm bullish on the price of the underlying, but I am also Vega positive. So I'm having an exposure also to volatility. And this is something that the trader does not want, because the trader has no views on implied volatility, so doesn't want to take a risk just randomly, okay? So the name of the game here is the following. The trader wants to achieve a position which remains delta positive, but at the same time has a limited Vega, possibly relatively close to 0. So I start by buying a call option, and I see that if I buy a call, I am delta positive and Vega positive. But then I say, look, I want to combine this with something else such that my final portfolio is going to be delta positive, but with a very small or possibly 0 Vega. How can we do that? First intuition. In order to have an overall 0 or close to 0 Vega, it's pretty clear that here we must have something which is delta Vega negative. First step. The second step is that in order to be Vega negative, which positions are conceptually available? If I consider buy call, buy put, sell call, sell put, which are the 2 positions out of these 4 which are Vega negative? We have seen earlier that I'm Vega negative whenever I sell options, okay? Because when I sell options, if volatility goes down, the option value goes down and the seller makes money. So here it must be sell something. What is the something that I should sell? Now, the apparently obvious answer here would be, let's sell a put option. But this is not the right answer here. Why sell? Well, it's not incorrect, but it's not the typical trading strategy with options here. Because selling the put options apparently would be just great, because if you sell a put, you are delta positive, so your delta becomes even larger, and you can reduce your Vega exposure. Why is this not working? For a pretty understandable reason, which is the following. Imagine what do you obtain if you buy a call plus sell a put. Let us consider first the case in which you have the same strike. Just graphically, this is the effect of buying a call. This is the P&L of selling the put option. It's pretty evident that the combination of the two would just be what? Would be a long future position. Okay? I cannot see your faces now, despite my incredible superpowers, but I would expect that not too many of you are truly surprised. If you buy a call and sell a put, you get a long future. That was the put call parity, okay? That we recently discussed. So, of course, if you buy a future, it's a strategy in which you are delta positive and you have no volatility exposure. The only problem is that this is not an option strategy at the end. At the end, you end up without options, in a sense, and having just a future position. If you instead choose different strikes, so if you buy call plus sell put with different strikes, then what happens is essentially the following. Here I have my long call. Let's say this one is my short put. Combination of the two looks like the following. And this position, which is okay, technically it's called the risk reversal. We are going to discuss it later on when talking about volatility. It is a strategy that can be done, but it is typically done for different reasons than playing on the price of the underlying. The unpleasant thing of this strategy, as opposed to the one that we are going to discover soon, is that, for instance, it still has unlimited losses, okay? Whereas there is something better that we are going to show you that has limited losses, limited profits, and is much nicer in terms of risk profile, because it's less risky than this kind of strategy. What is the strategy that we can go for is actually to combine something in which I have to sell in order to be delta negative, but what I sell is another call. How it is possible, you can ask me? Because if you sell a call option, then you're going to be delta negative. That's correct. So the trick is making sure that you buy a call option with a higher delta and you sell a call option with a lower delta. In this way, overall delta is going to be positive, and still you can balance your Vega. Let me show how this works. The idea is that you buy a call option with a lower strike. If you have a low strike for the call, it means that the strike price is going to be a fantastic price to buy, and the option is going to be a lot in the money, ideally, and so with a high delta. And you sell a call option with a higher strike. By selling that with a higher strike, it means that it is less in the money, or maybe even out of the money, and in any case with a smaller delta. The combination of these two options, with these two call options with different strikes, is called a bull spread. That's the name of the trading strategy. It is a spread because you are buying and selling two things which are pretty similar. Two call options on the same asset on the same maturity, just a different strike. And it is a bull spread because the position is bullish. The opposite case, when you do that with a delta negative orientation, it's going to be a bear spread because it is bearish. The easiest way to think about it, the most typical case, is the case in which you are long an in-the-money call and short an out-of-the-money call. It is super simple here to get that you're making something which is delta positive, because think about it. If you have an in-the-money call, the delta of this call option has to be higher or lower than 0.5. If it is in the money, it's going to be higher. So imagine it's going to be in the range between 0.5 and 1. So imagine, for instance, it has a delta of 0.6, and since you buy, this is multiplied by +1. Then on the out of the money option, the delta has to be in which range? Between 0 and 0.5. So imagine it's 0.4, and it is multiplied by -1 because you sell. So it's pretty easy to see that if this is the case, you end up with an overall positive delta. Have I been clear? That's the intuition. Let us try to understand better how the bull spread works. In order to do that, let us imagine to build the bull spread using the set of prices we used already. So imagine we buy the call maturity June on with a 109 strike, which has a cost of 2.63, and we sell the call option strike 111 with a premium of 155. Okay? It's pretty easy to see that with the future at 110, this call is in the money and this is out. Okay? So now in your next slide, you have directly the final graph. If you want to look at that for a second, take a blank sheet and let us try to build it together. So the point, just 1 second, let me quickly change. A second, the set of slides just to get the one where I have the blank slide on top. One second. Okay. So in what we are doing is we are combining a long 109 call with a premium of 263 and a short 111 call with a premium of 1.55. So relative to what happens to the future price, I want to draw the P&L of each of the two positions and then the two positions combined. Let's say that 109 is here, 111 is here. First part of the story is the purchase of the 109 call. Until 109, what happens is that I lose the premium, okay? And the option is not exercised. For prices greater than 109, I start exercising the option, and things go better and better. So this is the long 109 call. Second part of the story is the short 111 put. And until the future price at maturity is 111, what happens is that I simply get the premium as a profit. From 111 onwards, things start go worse because I have the other counterparty exercising until I have a potentially large loss. So this is the short 111 put, okay? Now, if we want to combine the two and see what is happening overall, first of all, let us see what happens in this range of prices, so below 109. Below 109, neither of the two options is exercised, okay? What happens? Do I lose money or make money? What happens is that I lose money. Why? Because the option that I buy is more expensive than the option that I sell. And the loss that I face is precisely the difference between the two premia. So what I lose is minus 1.08, which is the difference between minus 263 and plus 155. Is this clear? And this is what happens until I am at a price of 109. Second part of the story, what is happening between 109 and 111? Things are going better because I'm exercising my call option, whereas the other option is not exercisable yet. So I go up with a 45-degree line here. Now, the question I'm asking you is the following. How much money do I do if the future is at 111 at maturity? There are intuitively two components. Component number one is that I have a negative difference between the premia, which is minus 1.08. And this is on the negative side. However, what happens on the future? You have bought the 109 call. Do you exercise it if the future trades 111 and you can buy it 109? Certainly, yes. So, as a second component, you exercise the call and you pay 109. And then you do what? By exercising the call, you get one future, and the future trades at 111. So the other thing is that you sell the future. The combination of these is a profit of 2. So the overall result is a profit of 0.92, which is the combination of minus 1.08 in terms of difference of premium and plus 2, which is the profit on the future. I hope I've been sufficiently clear. Third part of the story, what happens for future prices greater than 111? Do I make more money? The answer is no. From this point onwards, I would have a stable profit. Why do I have a stable profit? I can see that in two ways. The first one is that from this point on, for every extra euro, the long call is making 1 extra euro, but the short put is losing 1 extra euro. And the two effects are compensating. The second thing is that even if the future were trading, say, at 120, a greater future price does not allow me to sell at a higher price the future. Because if the future trades 120, then what happens is that there is the exercise of the sold call, and then you have to deliver the future always at 111, which is the exercise price of the call options that you have sold. So there is no way whatsoever for you to make money more than that, even if the price of the future is larger. This is the intuition. So this is the final value that we get. We have a loss of 1.08 here and a profit of 0.92 on the other extreme. But as you see, this strategy is nicer because it has a limited profit and a limited loss as well. So it's a nicer strategy to be considered as opposed to some other ones that we have seen. You can take a directional position without risking too much, incidentally. And pretty clearly, the distance between the maximum loss and the maximum profit has to be equal to 2, which is exactly the distance between the two strikes, okay? Now, let us make some extra step. First extra step is, which is the overall behavior in terms of the Greeks of this position? So, let me write it again. What we are doing is that we are long a 109 call, and we are short a 111 call. Imagine I want to capture what is happening on delta, gamma, Vega, and theta. On theta, I must add a note. So here we are considering the simpler theta on options on Bund future, which is very nice, neat, and symmetric. So what we are going to say here does not apply to all possible option types. And what I would like you to reason about with me is the following. Consider which are going to be the Greeks under 3 different levels of the price of the underlying. So 110, 109, sorry, 110, and 111. What can we say about the Greeks in these 3 different situations? First and simple thing to be said. Delta is going to be positive in all cases. Why? Because I'm always buying a call option with a lower strike than the option of the call that I sell. So irrespective of where the future price is, the 109 call is either going to be more in the money than the other or less out of the money, but in any case, it must have a higher delta, and as a consequence, delta has to be positive anyway. What happens with the other Greeks? For instance, let us think about gamma. And first, let us consider what happens when the future trades at 110. Take a second to think about what is the sign of gamma for these 2 options. When is gamma positive? Remember that gamma means having a convex function, having the curvature that plays in your favor. You are gamma positive when you do what? When you buy or when you sell options? You are gamma positive when you buy options, okay? When you buy options. So you are gamma positive in this case, and you are gamma negative in the other case here. So you're going to have some balance between the two. How clear is this balance? Well, the point is, remember how gamma behaves relative to the moneyness of the option. So again, 1 is where the option is at the money. Gamma, which is the curvature, has its peak when the option is at the money, okay? So consider first the case in which the future trades at 110. When the future trades at 110, here you have two strikes which are symmetric relative to the at-the-money. It means that you are picking one option here and the other option there. And if the gamma is sufficiently symmetric, it means that the two values of the gamma are basically in absolute value identical. And since one is positive and the other is negative, you end up having a gamma which is basically zero. Have I been clear? However, think about what happens if the future trades at 109. If the future trades at 109, gamma is going to be now either positive or negative, because one of the two options is going to have a higher gamma. Take 30 seconds to think about which of the two has the higher gamma, and as a consequence, whether gamma is positive or negative. Let us see whether polls work. Take a couple of seconds, well, 5 seconds more to think, and then you can answer on the poll, and then we see what's going to be right. All right, apologies for the problem with the poll. It has worked in one class and not working in the other two. Can you see the poll now? Or you can't select it either? All right. Now, let us try to reason together. The idea here is the following. If the future trades at 109, how are the two options? If the future is at 109, the long 109 call is at the money. And being at the money, it has exactly the peak gamma. So the gamma of the at the money option wins. Since the gamma of the at the money option happens to be positive, overall, you're going to be gamma positive here. Instead, if the future went up to 111, at 111, the short call would become at the money, and as a consequence would have the highest gamma in absolute value. And since the short call is gamma negative, then you would have a negative overall gamma. This is the intuition. What happens with Vega? When are you Vega positive? When you buy options or when you sell? Vega means that, Vega positive means you make money, volatility goes up. As we've just seen at the beginning of today's class, Vega is positive when you buy. So you're Vega positive here and negative on the other call, okay? And Vega also behaves more or less in the same way. So it's maximum at the money and goes up sort of symmetrically. As a consequence, Vega behaves exactly in the same way. So here you're Vega with 0. If here you end up, here you have a positive Vega because the at the money option is the 109 and it wins. At 111, the option that you sell, which is negative Vega, wins. What happens now with theta in the simplified case in which we have options on a Bund future? First of all, if we associate being theta positive with the idea that I make money when time passes, theta is positive for the option buyer or for the option seller? Think about it 2 seconds before I give the answer. With theta, theta is positive for the seller, okay? And instead, typically, the buyer loses money when time passes. So these are the signs which are inverted. From the point of view of the behavior of theta, relative again to the moneyness, theta works more or less in this way, especially for options on Bund futures. So you have the maximum theta in absolute value again for the add money case. What is the consequence? If the future is at 110, theta is close to 0, because you have two opposite thetas that balance each other. Think what happens if you are here at 109. At 109, which option has the highest theta in absolute value? Again, the option which is at the money. But the option which is at the money has now a negative theta. So for theta, it is inverted. You have negative theta here and positive theta there. Okay? This is a good example of how you have the same trading strategy, but the risk profile changes a bit depending on where is the price of the underlying. Now, hoping that this is clear, and if it is not, my suggestion is try to review it and try to reason it step by step, and then listen to the video to understand which was the reasoning behind. Let me add another intuition which hopefully should help. If it doesn't, you can forget about my next 3 minutes and just get back to the table we saw earlier. So this is the P&L of the bull spread at maturity that we had before. Minus 108 plus 0.92, okay? And this was coming up by summing the P&L at maturity of the long call plus the P&L at maturity of the short call. What happens if instead we sum the P&L of the two options before maturity? So ideally, if you add this curve expressing the value of the long call before maturity with this curve expressing the value of the short call before maturity. If you did that, you would end up having this sort of graph. Okay? So imagine this could be the P&L of the bull spread today. And if we get closer and closer to maturity, think about what happens here. You get closer and closer to the final P&L line, okay? Which means that after some time, you would have this behavior here and this behavior with the curve going up in this situation, okay? Now, this gives you the intuition about how you have a change in the situation of the Greeks. So unfortunately, I cannot point out to the blackboard as I would do in a common class, but let's call this range of prices A, so the one below 110, and this range of prices B over 110. First question is, look at the curvature. If we want to see the sign of gamma, we can think about it from a graphical standpoint as whether you have a positive or negative second derivative looking graphically at the shape of the curve. In region A, are you gamma positive or are you gamma negative? Look at the graph. In this region, I have a U-shaped function, I'm gamma positive. In region B, I have an inverse U-shaped function, I'm gamma negative. As you see, I turn positive to negative as I cross 110, okay? Which was exactly what we see from here. It starts from being gamma positive and then becomes gamma negative, okay? Now, the fact of what happens if I move closer to maturity gives you the intuition about the theta. If you are in region A, as time passes, the P&L moves down. It means that you are losing money as time passes, okay? So here you are theta negative. Instead, when you are here, as time passes, you move up. So here you must be theta positive. Just to clarify from a teaching strategy perspective, I'm not saying that having the ability to plot these graphs is the best way to learn, okay? This is something that is not going to be possible, especially if you have multiple options. And I don't expect you to be able to do that in 2 seconds, and even not in 2 minutes, okay? I'm only giving you the sense that if you made a plot on Excel, this is what you would find, and this is consistent with what you can possibly understand, which is reconstructing this table. So reconstructing this table is something I expect you to be able to do, based on what you know on the Greeks, especially if you review the Greeks part over time, okay? Finally, in terms of volatility, if you want to get a crude intuition about it, think about it. Imagine the price were here, for instance. Imagine you were here at some distance from maturity. And if you allow me to make one of my silly examples, imagine you meet the genius of the lamp that, as in Aladdin, that gives you the chance of deciding whether you want to double the level of volatility from now to the end of the life of the option, or to freeze the volatility to 0. Of course, this is not possibly the best thing you would ask to the genius, but it's a limited genius that can only have an impact on volatility, okay? If you are at 109, think about what happens there if the price does not move any longer until maturity. You end up here in the point in which you have the maximum loss, if the price does not move left or right any moment from now on, okay? So intuitively, if you were there, you would prefer to double volatility rather than to freeze volatility to 0. The intuition I'm making is that in this region, you must be Vega positive. You prefer higher volatility because if the price does not move, you are ending up with a maximum loss. Instead, if you were here, with the price, say, above 111, if you could choose between having double volatility or freezing volatility to 0, you would like to freeze volatility to 0. So here, intuitively, you must be Vega negative. Lower volatility would be better, because you're in the region in which if the price stops there, you're going to have the maximum profit. This is just in terms of crude intuition. So here, what you have is just a simpler slide in which I'm just pointing out that the position is not always gamma or Vega theta neutral. So, for instance, if you buy the 109 call, sell the 111 call, when the future is 110, then gamma is 0. But if the future moves up, then the short option becomes at the money, so gamma is positive or negative, and the same happens when the future drops. If you have in mind the table that we just built, that's of course far, far better, okay? So the table is the full development of what here is synthesized quite crudely. As an extra step, sometimes you can even, not only if the price moves, the strategy which is perfectly balanced from a point of view of the other Greeks becomes unbalanced, but sometimes you can even choose the strikes precisely in such a way that the position is slightly Vega and gamma positive or negative. And this gives me the chance to ask you to run a small exercise. So I'm going to explain the exercise, stop for 2 minutes. You can work for 2 minutes trying to solve it, and then we see the solution. It's a way of working on the Greeks to getting to the closest possible extent to what I would have done with you in class, given actual conditions. So imagine that you can trade only call options with strike 140, 141, and 142, when the future trades 141. So you have a set of 3 prices around, centered on the current future price. What I'm asking you is the following, is to build a bull spread which is slightly Vega negative. So not with a 0 Vega, but with a small negative Vega. Which are the candidates? The candidates are the 3 bull spreads that you can make with these strikes, which is either long 140, short 141 call, or long 141, short 142, or long 140, short 142 call. Now, what I'm kindly ask you is the following. Just copy these 3 A, B, and C opportunities. Copy the fact that the future trades 141, and then you can take a couple of minutes to tell me whether A, B, or C is the right solution. I will hide the screen in a couple of seconds and set up another poll for that, and then the answer is going to be simply A, B, or C. Okay, let us see the poll. Well, there is a prevalence of A with some uncertainty still being there. So let me discuss the solution here together. The idea is, first of all, that there is one that we can exclude quite quickly. Well, the premise is it's more important that you try and make a mistake than not trying. That's the key thing. So everybody who's tried has done the right thing. Because if you understand why there is a mistake, that's a good way to make a step forward. So how would I reason here on this? First, I would say it's not going to be this one. Why? Because the 2 strikes are symmetric to the current price. So this for sure has a Vega which is equal to 0. It must be one of the other 2. And the second part of the story is, if you want to have a negative Vega, it means that the option with the negative Vega must have the highest Vega in absolute value, and therefore must be at the money. So you must be selling the 141 call because this one is at the money, and as a consequence, you are selling the option with the maximum Vega. So this is why the correct answer is A. That's the logic, okay? Second step, we can build a bull spread also with put options. So, for instance, we can use the 109 put and the 111 put option. One exercise that I suggest you to do is to reconstruct the P&L at maturity of the bull spread made up with put options using these 2 as I did earlier with the call options, okay? It's a nice exercise that helps. How can we get in 1 second, if we want to make a bull spread, which is the option between these two that we must buy and which is the option that we must sell? It's pretty simple. The right way to understand quickly which is the bull spread is thinking about the delta. Now, if the future trades 110, 15, which of these two options is the in-the-money put? Which of these two strikes is a good price to sell, given that it's a put option? 109 or 111? The one which is in the money is the 111. 111 is a great price to sell if the market trades 110, whereas instead this one is out of the money. Okay? So, second step, the delta of the first option is going to be between 0 and minus 0.5. The delta of the second option is going to be between minus 0.5 and minus 1. Okay? If you want to have a bull spread, you must have an overall positive delta. Okay? So now think about quickly, if you want an overall positive delta, what do you have to do with the put option with the larger delta in absolute value? Should you buy or sell this one in order to have an overall positive delta? You can answer through the chat. Correct. What you must do is that you must sell. Because if you sell, exactly what you get is that you sell the position which has the higher delta in absolute value. If the short put is the one with a higher delta in absolute value, which is negative, it becomes a large positive delta position. Okay? So, in other words, with the put, the short put is the delta positive part of the story. The long put is the delta negative part of the story. If you want to be overall delta positive, it means that this delta in absolute value should be larger. So the option that you sell should be the in-the-money one. So the right strategy, as you can see, is to buy the put 109, sell the put 111. As I told you, I would suggest you to go with the exercise of building the P&L at maturity. I'm now directly jumping to what you're going to find in your exercise, which is if you do that tonight, you're going to discover that you have a maximum loss of 1.08 and a maximum profit of 0.92. These two numbers should look relatively familiar. Why? Because they are exactly the same numbers we had here, with the bull spread made up with calls. Okay? So we are obtaining with calls and puts exactly the same profile at maturity. But why is this the case? This is not random. This happens because we have taken prices in which the put-call parity is holding in a fantastic manner. If you remember, the set of prices behind that is the one I used first for the put-call parity story. What is the implication I want to make clear? The implication is the following. If the put-call parity holds perfectly, then making a bull spread made up with calls or with puts is identical. You can roll the dices, or if you are a call lover, use call options. If you are a put lover, use put options, okay? However, if instead the put-call parity does not hold perfectly, or if there are bid-ask spreads on options so that the prices are slightly misaligned, you can't go through the full arbitrage, but they are not, the prices, relative prices are not perfect, then using calls or using puts may lead you to slightly different bull spreads. So essentially, you could end up where one bull spread works in this way, and for instance, if you do that with the other couple of options, you get something which is slightly translated upwards maybe by 2 cents, but it's 2 cents better for any possible price. So in this case, you have to try and see which of the two is better, okay? If put call parity does not hold perfectly, or there are bidder spreads making arbitrage is difficult, maybe having a bull spread made in one way rather than the other is slightly improving your position. That was the key practical message. What is a bear spread? A bear spread is simply the opposite. So if you, in a bull spread, you buy the in-the-money call, sell the out-of-the-money call. If you invert it, you sell the in-the-money call, buy the out-of-the-money call, you get the opposite, which is a bear spread. And in the same way, you can invert it with put options. Same specular story to what we've seen already. So you have a negative delta, clearly, and you have a Vega and gamma and also theta, which are small and tend to be very close to zero if the strikes are balanced. So even with the bear spread, I could potentially draw a table such as the one we did before with 109, 110, 111. I don't do that because it would be boring for you, but potentially you can do that if you want as an exercise, because it's simply specular story relative to what we've seen there. This is the graph that we obtain with the bear spread, which is just specular as opposed to the one that we have with the bull spread. In this case, it is combined by selling an in-the-money call and buying an out-of-the-money call. Now, let us finish with just a couple of exercises. The first one is the following. Imagine I give you a spread which is composed by a long 120 put and a short 123 put option, when the future trades 121. So you can get that the future price is trading not symmetrically, so Greeks are not going to be balanced perfectly. What I'm asking you, and you have 2 minutes to answer, are two things combined. The first one, is it a bear spread or a bull spread? Suggestion, think about what is the delta in order to answer. And second thing, which is the sign of gamma? So please again take note of the data. I'm repeating them if you want to take a note so that I build the poll in the meantime. Long 120 put plus short 123 put when the future trades 121. And I want to understand whether it's a bear spread gamma positive, bear spread gamma negative, bull spread gamma positive, or bull spread gamma negative. That's the type of answer. All right. Okay, other 5 seconds. Okay, there is some dispersion in answer, which can be understandable, and I'm not worried about it. Let us see about which is going to be the solution here. So first part of the story, is it a bull or a bear spread? In order to understand that, we have to see the long 120 put is out of the money, and this is our delta negative position. So the delta negative is a small negative delta because the put option is out of the money. Instead, the short 123 put, which is our delta positive position because it's a put option that I sell, is in the money. So it's going to have a relatively larger delta. It's a delta which is between minus 0.5 and minus 1 multiplied by minus 1, so becomes a delta which is larger than 0.5. As a consequence, overall, the positive delta of the short 123 wins, and I'm delta positive. Second part of the story, since the long 120 put is closer to at the money than the other one, and at the money you have a peak gamma, the gamma of the long 120 put, which is positive, is higher. So overall, the put spread is gamma positive. Okay? That's the kind of reasoning that is possible here. And of course, you can imagine a number of self-answers that you can make yourself to become faster and more profound in reasoning on that. Last thing is an exercise for you, not now, because now we are finished. For the next time, we are going to start next time by seeing the answer, which is the following. Consider two spreads when the future is 131, having symmetrical strikes, 130 and 132, 121 and 29 versus 133. So there is a wider distance from the strikes in the second case. Two questions. The first one is, are they bull spreads or bear spreads? And the second one, which of the two positions is riskier? And the way to answer that is think about the delta. Think about which of the two positions has a higher delta, whether A or B. All right? We are going to restart on Thursday. First thing is by seeing the answer to this, and then we are going to move into the world of volatility trading. Thank you for tonight. I hope the polls have helped a bit in keeping this some interaction. At least I tried. I hope you appreciate at least the effort. And this is what I'm going to try also in the next classes, unless you tell me that is a total disaster. All right, have a nice evening and see you on Thursday.